Good day, class. In this lesson, I would like to give you a little background, introduce you to exponential and logarithmic equations. Then we can look at some examples of solving exponential and logarithmic equations. So for the background, I always like to think about compound interest, which at this point you're probably very familiar with. Calculating compound interest, you have a formula, you identify your principal, your rate, and the number of times you've compounded, and you insert those items into the formula, and you discover that at the end of your interest accruing period, you'll have a certain amount in a given account if we're talking about money. So in this case, we have we're looking for the amount, that's our A, that we'll obtain when $2,000 is invested at 8% interest, and we're compounded annually for 5 years. So no problem, we discover at the end of that 5-year period we have $2,960.49. However, notice how here I'm asked to find the number of years needed to obtain this $2,960. I kind of just reutilize the same example. And we would use the formula for finding compound interest, but notice how we're substituting here, and notice what happens. We're left with a variable in the superscript, which is why we use one of the many reasons why we'll use a logarithm and find it very useful. In fact, a logarithm is a quantity to which a number can be raised to obtain a desired value. So the logarithm is actually that quantity to which we'll raise that number. So in this case, we already know it's about 5, but even so, that is by essence, by nature, by definition, what a logarithm can be considered. So let's think about where some of this material has come from. We're familiar with calculating the log in our calculators, and so you see here off to the right I have the log of 1.72. And so what I want you to appreciate is that what our calculators are doing, they're actually multiplying for us the many times, however many times we need to multiply whatever number. But a fellow by the name of Napier, many years ago, a Scottish fella, he calculated, I hear, 10 million logarithms, and it took him about 20 years to do that. I don't know how much truth is in that, but I do know that someone had to sit down and calculate all these by hand and do the actual multiplication of these decimals. So we have here what we used to use prior to the calculators, a table of logs. And so if I'm looking for the log of 1.72 on my table, I'll visit 1.7 on the left. I'll visit 2 hundredths on the in my vertical my column, and then I discover where those meet, which is the same as what I get in my calculator, the 2.355. You could round that. Here we're rounded to the 4 decimal places. So what I want you to appreciate here is that a log is a constant value, and it's the result of multiplication. Really, what's happening, to what number do we need to raise a base to get a desired outcome? And that is the nature of a logarithm. That is what a logarithm represents. And so we can easily find the log of 1.72 either using our calculators or using our a log table. I also want you to know that regarding exponentials we see on the left and logarithms we see in the red on the right, we have symmetry. Remember, we talked quite a bit about symmetry or an equation, graph, and a table kind of saying the same thing, representing the same information. We can see here that exponentials and logarithms are symmetric. In this case, we see that y is equal to 5 raised to the x power. This is an exponential. If you were to sit down and sort of multiply this out, you get that blue line, that exponential growth that sort of you might already be familiar with. We're just like shooting up all of a sudden, and you can kind of see how this graph is behaving. Notice this is a computer generated graph that I've done here, but please note that blue line does not actually touch. It never actually meets 0 on the y-axis, so be advised of that. And then I have the graph of y equals log base 5 of x, and we can see that it is symmetric with the graph of y is equal to 5 raised to the x power, and those have symmetry across that y equals x line. And so this symmetry sort of plays out both in the equations, graphs, tables, whatever. You'll find this symmetry, and it's going to be very useful when you pursue solving exponential and logarithmic equations. And a quick note here, we talked about the logarithm being a quantity by which a base can be raised to achieve that desired amount. But notice here we still have a notation that we have to be thoughtful about. On the left, we have 2 raised to the 4th power is equal to 16, or is 16. And on the right, we have log base 2 of 16 is 4. And remember what the log is asking us, that 2, it's asking us about that base 2. To what power can we raise it to get 16? And so the solution there would be 4. It's just notation. It's the way it's mathematicians have determined that we're going to write this. So we just sort of go with it, and we don't panic. We still recognize that a logarithm is a quantity. It is a constant value. And so we also are respectful of natural logarithms as well, because you've heard of that at this point, and just recognize it is also a quantity by which a number can be raised to achieve a desired outcome, but it's about the base e, a quantity by which base e can be raised to achieve a desired outcome. So let's think about that for a minute, because it's really important to sort of appreciate the number e. It's a really important number. On the left, we have 2 raised to the 0 power is 1. We're familiar with that. On the right, we have log base e of 1 is equal to 0. Really, on the right, we have e raised to the 0 power is what's going to give us a 1. And we know any number raised to the 0 power is 1. But notice how the natural log of e is 1. We know that the natural log of e is 1, first off, by how the number e, what the number e represents, which I'll help you recognize that in just a moment. But we're going to be looking for this ln of e when we're solving exponential, and when we're solving our log equations, because we're going to recognize when we're dealing with the number e that we can use a natural log to work with it, because the base, the understood base of a natural log is e, and this is the notation that we use, and we're actually saying e raised to the 1st power here is e. Okay, so, and we know that any number raised to the 1st power is that same number. And so we want to be thoughtful about how we're dealing with raising numbers to a power. Notice here off to the left, I just put a little side note to remind you of or evidence the reason that a number raised to the 0 power is 1. It makes 1. Any number raised to the 0 power is 1. So you can just pause that video if you need, pause this video if you need, and just remind yourself that any number raised to the 0 power is 1. So then, if I can help you understand what e is before we really start to work with it and play with it, I want to go back to the example where I talked about the compound interest. So remember, we did the quick example. The amount 2,000 is getting raised to or the amount we accrue in this situation when we're compounding interest semi-annually. And so what happens though if we compound monthly? Notice how I want to get more money. I want to get it faster. And so I start with the banker, and they're compounding twice a year, and I go into that bank and I say, hey, can you compound 12 times a year? So notice what happens with my equation. I change that compounding to monthly, so we're happening 12 times a year, but I only go from $2,960 to $2,979. Not quite the jump I'd hoped. So I'm really going to try to pump up the volume, maybe compound annually, pardon me, daily. And I notice nothing really significant has happened here. I'm only now at 2,000. I'm still at 2,900. I still haven't even cleared 3,000 after all this extra compounding. And in fact, you can continuously compound and realize that you will approach, in fact, the number e. So the number e is a constant value, and here's a way to sort of draw it out and express why that number is so important and special. So one of the reasons, notice how if you want to do a calculator exercise, you can play with this formula here on the left, 1 plus 1 divided by x, that quantity raised to the power of x, and you notice that the growth just doesn't happen. As much as you want that to get bigger and bigger, you can raise up that x to infinity and you still are not going to get much bigger. In fact, you're approaching the number e, which is an irrational number which continues on into infinity with multiple digits, different digits. And so it is an irrational number, but it is a very important number because we recognize that within the context of compound interest, if I can sort of stay there, we're dealing with that growth and how we sort of, to some extent, max out when we're dealing with money. So we're calling that the number e. Is a very special number. With that being said, we'll employ these laws in our next instructional video to demonstrate how we will solve exponential and logarithmic equations.